10:20 అయింది, లాగిన్ అవ్వండి. 10:20 అయితే తప్పు అది. 10:21. నేను ఇక్కడే ఉంటాను కదా, ఏదో పెట్టేసి ఎక్కడ ఇదేసి
మన ఇద్దరం వచ్చినట్టున్నాం సార్. ఆయన ఎవరు ఇంకొక ఆర్ఎల్సి అప్పారావు గారు వచ్చాడు, ఆయన ఉన్నాడు. అప్పారావు గారు,
సార్ గుడ్ మార్నింగ్ సార్.
నమస్తే సార్. వినపడుతుందా?
వినిపిస్తుంది సార్.
ఓకే ఓకే
హ్యాపీ రిపబ్లిక్ డే సార్.
థ్యాంక్ యూ సార్, థ్యాంక్ యూ, సేమ్ టు యూ.
Morning, sir.
Good morning, sir. Good morning to everyone.
వెల్కమ్ అండి మరి రమేష్ గారు.
Sir, same to you, sir. Good morning, sir.
నమస్తే.
Ramanan garu.
ఎక్కడున్నారు?
నేను ఇంట్లో ఉన్నాను సార్.
ఇక్కడ ఉన్నారు. మరి జెండా వందనానికి రాలేదు.
నేను వెళ్ళొచ్చాను అక్కడికి ఆఫీస్ దానికి వెళ్ళి
ఆ,
జస్ట్ ఇంటికి వచ్చాను ఇప్పుడు.
ఓకే, వెరీ గుడ్. ఒక 5 నిమిషాలు ఆగి స్టార్ట్ చేద్దాం. ఏది మన సీతారాం బాబు గారు వచ్చినట్లేడు. వాళ్ళ సుబ్బారావు గారి తరఫున ఎవరైనా వచ్చారా?
యప్ నేను ఉన్నానండి. సుబ్బారావు గారి చిన్న పాపని.
నమస్తే అమ్మా. నమస్తే.
నమస్తే అండి.
నమస్తే సార్. నమస్తే.
నమస్తే సార్. ఏంటి మీ దర్శనాలు లేవు? సంవత్సరాలు దాటిపోయి 1 year అయింది అనుకుంటా.
మస్తు మంచిగా
లాస్ట్ ఇయర్ మార్చి లో కలిచాం. మళ్ళీ మార్చి రాబోతుంది.
పర్యటన నడుస్తున్నది అదే టైంలో పెట్టింది.
మేము కూడా లేదు 6 నెలలు. ఏమండి
సౌండ్
ఏం సార్ ఇనిషియేటివ్ రావట్లేదు రమణ సార్?
మీరు ఎప్పుడు వస్తారో చెప్తే మేము వస్తాము.
మేము ఏడే ఉన్నాం. నిన్న 4 రోజుల నుంచి ఎవ్రీడే ఐఎమ్ కమింగ్. టుడే ఆల్సో ఇక్కడ వచ్చాను నేను.
అచ్చా.
ఏంటి జాయిన్ అవ్వలేదు?
రాజుగారు కలిశారు 2-3 సార్లు. ISN
జాయిన్ అవుతున్నారా? మేము స్టార్ట్ చేయాలా? ఏం చెప్పారు?
వీళ్ళందరూ ఫోటోలు ఆన్ చేసుకోమని చెప్పండి.
వీడియో ఆన్ చేసుకుంటే
వీడియో
ఆనరీ సెక్రటరీ నాకు చెప్పకుండా ఆయన చైర్మన్ ఇప్పుడు ఆయన చెప్పాను. ఆయనే రావట్లేదు. ఆయన నాకు ఫోన్ చేసి నేను రావట్లేదు, నువ్వు కండక్ట్ చేయాలి.
మీ శిష్యుడు కదా.
ఓకే, విల్ స్టార్ట్ అండి మరి.
ఇద్దరు జనాలు ఇప్పుడు అమ్మాయి.
Good morning to everybody. I'm of course Reddy, immediate past chairman, presiding in place of Dr. Venkata Subbaya, who is not available today due to some urgent work. And I'm very, very happy because the great legendary engineer V. Subbarao garu 8th endowment lecture arranged by our Telangana State Center on the topic predicting the droughts using artificial neural network case studies, a case study by Dr. Nagamalleswara garu. So now, as a today's presiding officer in the seat of chairman, I hereby welcome the respected keynote speaker, Dr. B. Nagamalleswara garu, Professor and Head of the Department, Civil Engineering and Associate Dean, CVR College of Engineering, and Engineer P. Apparao, the Chairman of Ramagundam Local Center, Dr. K. Sitaram Babu, Honorary Secretary, Telangana State Center, Engineer Ramesh, Joint Honorary Secretary and Convener of this particular event of the day, and Dr. K. Srinivas Reddy, Honorary Secretary of Ramagundam Local, galaxy of eminent personalities who are online participants, and past presidents, past vice presidents, past chairman, past honorary secretaries, council members, committee members of institutional, and also corporate members of IEI, family members of late engineer Subba Rao garu, Madam Anuja garu is online, media friends, ladies and gentlemen, and good morning once again to everyone. And also I wish a happy Republic Day. Today, I feel it is a great privilege and honor to be amidst this August gathering and extend a warm and hearty welcome to the keynote speaker, Dr. B. Nagamaleshwar Rao garu, and all of you to this engineer Subba Rao 8th Endowment Lecture. We are very fortunate we have eminent personalities like Dr. B. Nagamaleshwar Rao garu, and we thank him for sparing his valuable time to amidst his important assignments for this coveted event. We are very fortunate to have him today, and I am very glad to inform that the Telangana State Center of the Institution of Engineers has been regularly organizing more than 21 endowment lectures every year on the birthdays in the honor of the eminent engineers like Engineer V. Subba Rao garu and Engineer M. Tirupati Reddy garu, Dr. K. Gopichand, Dr. J. Purushottam Endowment Lecture, Engineer G. Prabhakar, Engineer Koka Krishna Mohan Rao garu, Engineer S. Balakrishna Reddy Endowment Lecture, Engineer J.V. Subba Rao Endowment Lectures, T. Hanumanta Rao garu, Engineer A.P. Ranganatha Swami, Dr. S. Raghavachari, Dr. Narl Tata Rao garu, Engineer Matur Gopal Rao garu, Engineer Gurram Kotireddy garu, Engineer Atluri Venkateswar Rao garu, Engineer R.L. Raj garu, Dr. John A. Murray, Dr. N.V.R.L.N. Rao garu, Engineers L. Venkatakrishna Iyer, K.V. Srinivas Rao and M.L. Swami Endowment Lecture, and Dr. A. Ramakrishna Endowment Lecture, and Engineer I. Basavaraj Endowment Lecture. See, the endowment lectures are being delivered by people of high eminence with considerable professional experience to throw light on the important emerging topics of today's relevance. I take this opportunity to brief you about the great engineer, late engineer V. Subba Rao garu. V. Subba Rao garu obtained BE in 1965, M.Tech Water Resources in 1982, and M.Tech Environmental Engineering in 1986. He attended several training programs, including an orientation program for urban public health engineers at RAO University of Technology, United Kingdom, in the year 1991. And late engineer Subba Rao garu joined Public Health Engineering Department, AP in 1965, and rose to the position of Chief General Manager and retired in 2000. Attended to the investigation, execution, operation, maintenance of water supply schemes and sewerage treatment schemes. The credit goes to him for remodeling of sewerage systems of Hyderabad and Sikkim of 327 millions and remodeling the existing sewage treatment plant for Hyderabad at a cost of 43 millions and maintaining and operating it. Other important works carried out by him include urban water supply schemes for Warangal, Nizamabad, and sewerage for Guntur, and rural water supply schemes in Telangana region. Late Sri V. Subba Rao garu's areas of specialization of planning, designing, execution, operation, and maintenance of sewer systems, wastewater treatment plants, drinking water treatment plants, and modern techniques of measuring and billing for drinking water. And he has also authored the book titled Accounts for Engineers, a handbook, and published the book titled Tender Procedures, jointly with Engineer G.L. Rao, the past president of the Institution of Engineers, and participated in various conferences and also presented papers. Late Sri V. Subba Rao garu is a recipient of prestigious award, Engineer of the Year in 1997, jointly instituted by the government of AP and IEI, AP State Center at that time. took active part in various activities of IEI Hyderabad. He was Honorary Secretary of the then AP State Center, the Institution of Engineers, during the years 1998 to 2000. The Telangana State Center Committee, at its special meeting held on 27th May 2017, has agreed in principle to organize an immediate endowment lecture in the memory of V. SUBBA Garu, former Chief General Manager, Hyderabad Metro Water Sewerage Board, and past Honorary Secretary of IEI every year on 26th January, and present a medal and certificate to topper of the MTech NIT Warangal with first class for over 2 years in water resource engineering. Today, Telangana State Center arranged Engineer V. Subba Rao 8th Endowment Lecture on the theme predicting the droughts using artificial neural networks, a case study in association with the IEI Ramagundam Local Center. I am sure you are all anxiously waiting to hear the lecture from the eminent speaker, and thus I limiting myself and hope that you will really enjoy his talk. On behalf of the Telangana State Center of the IEI and on my own behalf, I once again extend a hearty welcome to the keynote speaker, Dr. B. Nagamalleswara Garu, Professor and Head of the Department of Civil Engineering and Associate Dean, CVR College of Engineering, and once again to all of you to this important event. Before I call for delivering the endowment lecture, Dr. V. Nagamalleswara Garu, I request Engineer Mari Ramesh, the FIE, the new convener of this event, to kindly introduce today's eminent speaker, Dr. V. Malleswara Garu. And thank you, one and all. And over to Engineer Mari Ramesh. ఇది స్పీకర్ ఆఫ్ లో ఉంది, స్పీకర్ ఆఫ్ లో ఉంది. మర్రి రమేష్ గారు.
Yes. Now is it okay, sir?
Yeah.
Is it okay?
Okay, sir. Is it okay? Now okay.
Okay. Right. Thank you.
Sir, it is not audible.
Ramesh garu, not audible. Again it has gone to, you open it. Yeah, audio is on now.
Is it okay, sir?
Yeah, now it is okay.
Okay, fine.
Again it has gone. You please keep it open.
Is it okay now?
Now it we are getting just again something. Okay, now it is okay. Speak.
My video is also okay, sir?
Now
Video?
you go on. Please continue.
I am Mari Ramesh, committee member and joint honorary secretary of IITSC. It's proud privilege for me to introduce Dr. B. Nagamalleswara Garu, who is the speaker for this today's Engineer V. Subba Rao Endowment Lecture. Dr. B. Nagamalleswara Rao is currently working as Professor and Head of Civil Engineering and Associate Dean in CVR College of Engineering, Hyderabad. He has vast experience of 30 years, out of which he has experience in teaching for 26 years and he experience in industry for 4 years. He did his Doctor of Philosophy from NIT Warangal and MTech in Water Resources and AMIE in Civil Engineering. He has awards like DST Young Scientist Fellowship in 2002 and also GM Navate Award for the best paper in 2004 by ICH. His publications and more than 52 journals and conferences he attended, and publications are 52. And his research projects, he completed 4 projects in IE, CTE, and 1 project in DST, and 1 project in UGC. He has attended 2 international conferences and organized national conferences 9 numbers, and a national workshop organized about 18. He visited many countries, out of which he visited Brisbane, Australia, and Bangkok, Thailand, to attend international conferences. His research areas are in GIS and fuzzy applications in watershed management, rainfall and runoff modeling, urban flooding, mapping, and modeling. He is also member of, apart from the Institute of Engineers India, is member of Indian INSAR Group, CSRE, IIT Bombay, and is life member of Indian Society for Technical Education, and is also life member for International Association of Hydrological Sciences, UK, and is also member of American Society of Civil Engineering. Thank you, one and all.
Thank you, sir. I request Dr. Nagamalleswara Rao garu to kindly deliver his keynote address, sir. And the subject is predicting the droughts using artificial neural networks, a case study. Sir, welcome, sir.
Yes, sir.
Yeah.
Good morning, respected members. It is an honor for me to deliver a lecture on this auspicious occasion as a water source engineer. I am also a fellow of Institute of Engineers, but I am not actively participating in your activities, sir. I am more of interest in academics. Okay, thank you for giving me the opportunity. So today my topic is predicting the droughts using artificial neural networks, a case study. So this is one of my research student project work. Research work is doing for his PhD. As a part of that, I'm presenting here. So with an objective of estimating drought severity in Gujarat, Daman, and Diu. Because you may ask why you are taking Gujarat and all. Because my student is from Gujarat. That is why he has taken the study area in and around Gujarat, Daman, and Diu. Not only estimating, we are trying to forecasting drought using artificial intelligence models, which is the talk of the day. Everybody wants to use your artificial intelligence, AI and MA models. Okay. You know that everybody knows the drought, it is not immediate. It may be very slowly it entering into our system, but it will have a long effect. So the content here is, I'm going to start with the introduction, literature review, methodology, and the analysis, the methods, what I'm adopting to predict the drought, and with the results, with the study area, and with our little discussion on my study. Drought is a natural disaster that affects society and the environment frequently. It significantly influences water resources availability, agricultural production, environmental health, and thus socio-economics of any region. There is no definite way of defining drought because it is not possible to determine the exact duration of a drought event. Drought slowly builds over time and leaves a prolonged influence over a large geographical space without any significant infrastructural damage. That's a big issue. We didn't identify drought is already entering into the system, because if it has any damage occur, like an earthquake or a cyclone, that effect is visible, but the drought effect is not immediately visible. The complexity of a drought event is characterized by its duration, intensity, and severity. In a simple term, drought is defined as the period of a temporary shortage of water resources due to persistently low precipitation. Drought can have different forms such as meteorological drought, hydrological drought, agricultural drought, and socio-economic drought. Meteorological droughts occur due to deficiency of precipitation from the average rainfall. So it is the initiator of all other kinds of droughts and therefore most widely studies of monitoring droughts. Meteorological drought frequency does not depend on the average precipitation of an area rather than the variability of precipitation. The large variability of precipitation on the deficiency side indicates drought. Therefore, it can occur in any climate region, including tropical region like India or humid climate zones. Even it can happen in Northeast India, the highest rainfall region of the world. A recent study suggests that the wetter parts of the earth would experience more devastating drought in future. It urges more attention to be given for monitoring and forecasting droughts in tropical regions. Droughts are often more devastating when it occurs in tropical region as the ecosystem of such region is habituated with higher annual rainfall. Improper drought prediction always results in poor drought management. Hence, there is a need to build fast, reliable, and accurate models for drought prediction, which can provide quantitative data on impending drought-related risks. So, with a small introduction, the recent past, the people who are worked on these models are either in the estimation or prediction drought model. Just I'm going to discuss 1 or 2 slides. Amir et al. 2013 in his paper, they used a multivariate, multi-index drought modeling approach proposed for concept of cupolas. Zhigang Ho and 2013 in his study outlines a multivariate, multi-index drought monitoring framework, namely the multivariate standard drought index, popularly known as MSDI, for describing droughts based on the states of precipitation and soil moisture. And Alexia Farhan et al. 2014 in his paper introduces the Standard Drought Analysis Toolbox, SDAT, that offers a generalized framework for deriving non-parametric, univariate, and multivariate standardized indices. Ravi Shah et al. 2015 in their paper, they list out the results of the Surat district and found that the results of SPIs and actual climate conditions have quite similar results as part of their respective categories. For example, -1 to -2 categories indicate moderately dry and arid drought year, including 1974 to 1995 of their study years. And Janaki Mahapatra et al. 2020, in their study, they demonstrated a programmatic scientific framework for predicting seasonal groundwater levels at a large scale using field measured data. Considering the research need and the data constraints in developing nations, 3 relatively powerful machine learning or artificial intelligence techniques were suggested. In the very recent years, that was last 10 years back, and in the recent years, Elizabeth Ludwig et al. In their paper titled Applying Machine Learning for Drought Prediction in a Perfect Model Framework Using Data from a Large Ensemble of Climate Situations. Researchers applied artificial neural networks to predict drought occurrences with a 1-month lead time in Munich and Lisbon. By incorporating 28 atmospheric and soil variables, the models achieved approximately 55 to 57% accuracy in classifying drought events. The study highlighted the significance of variables like the North Atlantic Oscillation Index and air pressure in drought prediction. In another paper, Alexander Marceau et al. In 2023, in their paper titled Long-Term Drought Prediction Using Deep Neural Networks Based on Geospatial Weather Data. This research introduced a spatio-temporal neural network model leveraging accessible monthly climate data to predict drought conditions up to a year in advance. The study found that transformer models such as Earth Farmers excelled in short-term forecasts up to 6 months, while convolutional LSTM models were more effective for long-term predictions. And in another paper, Xian Yu et al. In 2024, in their paper titled Multivariate Spatio-Temporal Modeling of Drought Prediction Using Graph Neural Networks. A novel approach was proposed employing a multivariate spatio-temporal sensitive network known as MSTSN that integrates geographical and temporal data. The model utilized graph neural networks to capture relationships between different areas and employed gated recurrent units with multi-head self-attention to enhance predictive capabilities. This is a very, very recent work by Pedro Josh Sahin et al. In 2024 in their paper Artificial Neural Networks for Drought Forecasting in the Central Region of State of Zacatecas, Mexico. This study utilized artificial neural networks to forecast numerical values of 3 drought indices: Standard Precipitation Index, SPI, Standard Precipitation and Evapotranspiration Index, SPEI, and Reconnaissance Drought Index, RDI, across different timescales like 3 months, 6 months, and 12 months. The findings indicated that the RDI was most effectively modeled by artificial neural networks, suggesting its suitability for drought forecasting in semi-arid regions. So, from the different researchers, we have selected 4 models to forecast, and first to estimate, and then to forecast the drought in the region, my study area. So the study area is Gujarat and of Union Territory of Daman and Diu. So Daman and Diu, formerly a Union Territory of India, we know that was merged with Dadra and Nagar Haveli in 2020 to form the Union Territory. So the location is latitude of 20 degrees 25 degrees north to 20 degrees 27 degrees north. Longitude of 72 degrees 49 degrees minutes east to 71 degrees 1 minute east. The total area having 112 square kilometers, Daman and Diu. The boundaries are Daman surrounded by Gujarat and Diu is isolated, located on the southern coast of the Gujarat. The climate condition is tropical climate. Summer during March to June, temperature varying from 28 to 38 degrees. Monsoons June to September, moderate to heavy rainfall. And winter November to February. And rivers, important rivers are Daman Ganga River, flows through Daman and meets the Arabian Sea, and Chase River, a seasonal river and Diu. And terrain is mostly flat with coastal plains, a mix of flatlands, low hills, and rocky coastline. Okay. And coming to the, that popularly Gujarat, having the Western India is 6th largest state by area and has longest coastline among Indian states. So the total area is 1,96,024 square kilometers and even ranked 6th largest India. Climate is tropical monsoon, semi-arid, and major rivers are Narmada River, longest river, longest river in Gujarat, Tapai, Sabarmati, Mahi, and Daman Ganga and Banaras River. Then major crops are cotton, groundnut, wheat, bajra, and sugarcane. Mineral resources like lignite, bauxite, limestone, and gypsum. Okay. So with this, the methodology what I'm adopting here is, I told you I'm going to take 4 indices. So a large number of DIMS drought indexes has been developed for monitoring droughts. Among all, the Standardized Precipitation Index, SPI, is the simplest, statistically robust, comprehensible, and independent of climate factors. Despite the recent introduction of SPI, it has been widely accepted in the drought prediction community as a useful drought index and has been used in numerous studies to investigate drought variability when assessing the impact of drought in agricultural and hydrological sectors. Several forecasting models have been introduced for forecasting droughts, such as auto-regression integrated moving average, ARIMA, multiple linear regression MLR, and Markov chain. SPI is a probabilistic index derived from a tailed distribution of rainfall deficient. Therefore, the scale of SPI is not linear because the rainfall is not linear. This has made the forecast of droughts using conventional statistical methods which are more challenging. Most recently, the application of artificial intelligence models have exhibited outstanding progress on modeling droughts, indices, and climatology. Several versions of AI models have been developed for SPI forecasting, including artificial neural networks, support vector regression, extreme learning machine, adaptive neurophagy interface system, M5 tree, random forest, linear genetic programming, least square support vector regression, extreme randomized tree, multivariate adaptive regression spline, wavelet pre-processing integrated AI models, and bio-inspired hybrid AI models. Although there have been diverse models introduced for modeling DIs, it is difficult to determine a generalized or a perfect model that can still all types of climates. Besides, there is a chance of misleading in model development if the non-appropriate variables of model structure are set up. Furthermore, every region behaves differently following the weather statistics and historical characteristics. The current research is devoted to the development of AI model for SPI forecasting for Western coastal India. So drought predicting using ANN involves several key stages, including data collection, pre-processing, model development, training, validation, and evaluation. Data collection and selection. The first step in gathering relevant hydrological and meteorological data sets essential for training the ANN model. The following variables are typically used. The input variables are precipitation in millimeters. It may be monthly or daily rainfall data, temperature in degrees centigrade, maximum temperature, minimum and mean temperatures, evapotranspiration, potential and actual evapotranspiration rates, soil moisture content in percentage, surface and subsurface moisture levels, vegetation index, NDVI, EVI, normalized difference vegetation index as an indicator of drought stress. Stream flow in meter cube per second, river discharge levels for hydrological drought monitoring. Atmospheric indices like EI El Nino Southern Oscillation, ENSO, North Atlantic Oscillation, NAO, and other climatic oscillations. And drought indices, the target variables are Standardized Precipitation Index, SPI, Standardized Precipitation Evaporation Index, SPEI, Palmer Drought Severity Index, PDSI, and Reconnaissance Drought Index, RDI. And the different data sources, what we have used are meteorological and climate data sets, global climate models, GCMs, which are available in the entire world. So once we have that model, you can find in a micro level, in a even 10 meter square area, also you can predict how the climatic conditions are available nowadays. And I mean, you know that remote sensing data from NRSA and NASA and other recent satellites reanalyzes data sets and local weather stations, and hydrological data from river gauging stations and soil moisture sensors. With this data, we require some pre-processing, data cleaning and handling misvalues. Interpolation techniques, I'm using some of the interpolation techniques to fill the gaps in the data sets using linear, planar, kriging interpolation to fill the gaps, and outlier removal, statistical methods, Z-square and IQR to detect and remove anomalies. And data normalization and transformation, minimum maximum normalization x scaled equal to x minus x minimum divided by x minus my x minimum, and standardization Z-square normalization, x scaled value equal to x minus mu by rho sigma. So here that 4 models what I'm using in this process, one is non-parametric multi-index drought monitoring method, empirical probability method, ANN model, SPI, SSI, MSDIE, MSA, DPN models. So I have explained here below what is SPI, SSI. SSI standardized soil moisture index, MSIDE multivariate standardized drought index empirically, MSDIP multivariate standardized drought index parametrically. Now I am going to explain one in each method. What is that method defines, how to find the index, what is the data required, what are the limitations. 4 methods, then we are going for the actual results of my work. So non-parametric multi-index drought monitoring method, first method. Drought is a complex natural hazard characterized by a prolonged period of water shortage. Monitoring drought condition is essentially for managing water sources, mitigating its effects, and implementing timely response measures. Traditional drought monitoring methods often rely on single drought index or parametric values approaches, which may not fully capture the variability of drought conditions across different regions. To address this limitation, the non-parametric multi-index drought monitoring method integrates multiple drought indices without assuming any predefined statistical distribution, making it more robust and adaptive to diverse climatic and hydrological conditions. Non-parametric versus parametric. Parametric methods assumes that the data follows a specific probability distribution, example, normal distribution, gamma distribution, or log normal distribution, which are very common. Common examples includes the standardized precipitation index and the Palmer drought severity index. Non-parametric methods, on the other hand, do not assume any underlying statistical distribution, making them suitable for heterogeneous and non-stationary climate data. The non-parametric multi-index approach is advantageous because it handles skewed and non-normally distributed data more effectively, combines multiple drought indicators for a more comprehensive assessment, improve accuracy and reliability in diverse climate regions. The components of the multi-index approach are: it integrates various drought indicators to provide a holistic assessment of drought conditions. Some commonly used indices include meteorological drought indicators. In that, again, SPI based on precipitation anomalies, and SPEI incorporates both precipitation and evapotranspiration. And hydrological drought indicators, stream drought index, SDI, measures the impact of drought on river flows, and reservoir storage index, RSI, evaluates the decline in water storage in reservoirs. And agricultural drought indicators by vegetation condition index, VCI, derived from remote sensing data from NDVI data, soil moisture anomaly, SMA, assesses soil moisture deficiencies. And fourth one, socioeconomic indicators, water supply deficit index, measures water availability for human consumption. And crop yield anomaly, CYA, evaluates the impact of drought on agricultural production. By integrating these indices using a non-parametric approach, the NP-MIDM method offers a comprehensive and unbiased assessment of drought conditions. The methodology of non-parametric multi-index drought monitoring includes: first step, data collection and pre-processing. Gather multi-source data, precipitation, temperature, soil moisture, stream flow, satellite data. Normalize the data using rank-based methods like empirical cumulative distribution function. And second step, ranking and weightage in the index is important step. Each drought index is ranked separately without assuming a specific probability distribution. After that, weighing can be performed using entropy weighing method or principal component analysis to determine the relative importance of each index. And the third step, aggregation of indices. Non-parametric statistical techniques such as kernel density estimation or quantile-based aggregation methods are used to merge different indices. And composite drought index, CDI, is derived using methods like median ranking approach, fuzzy logic based integration, machine learning techniques, random forest, and neural networks. And fourth step, classification of drought severity. The final drought severity classification is determined based on thresholds derived from historical data. That is mild drought, 20th to 40th percentile, moderate drought, 10th to 20th percentile, severe drought, 5 to 10 percentile, and extreme drought below 5 percentile. And last step, spatial and temporal analysis. GIS and remote sensing tools nowadays, which are available very widely, are used to know temporally to what extent the effect of drought will be, severity will be there, and you can generate severity maps, and which is useful for the managers like at state level, at district level, or state level, or even village level. What are the areas are going to be affected and what are the measures to be adopted in advance. and the time series analysis is performed to track drought evaluation over different seasons and years. But the challenges and in this method are, despite the advantages, the non-parametric multi-index drought monitoring methods faces some challenges like data availability, requires high quality and multi-source data sets. Computational complexity involves integrating large data sets and advanced statistical models, and regional adoption needs customization based on specific climate and hydrological conditions of the country as well as the states. So whatever I explained the method in nutshell, this is the equation in the equation form what I've adopted. So here I'm going to estimate precipitation deficit and soil moisture deficit indexes. My time steps are 1 month and 6 months. I have divided the data and into 1 month. Within 1 month, what is the things happen? Within 6 months, how the precipitation deficiency and soil deficiency may occur. So in the MSDI based joint probability, I defined MSDI equal to phi inverse pi, and where pi denotes the joint probability of precipitation and soil moisture, and pi normal standard distribution of the data. And next one, the joint distribution of two variables can be expressed as probability of x less than or equal to x, y less than y equal to p. Okay. So this mathematically, this is the equation what I am using for non-parametric multi-index approach monitoring method. And the second method what adopted is empirical joint probability method. When dealing with two or more events, because generally if you estimate the drought, generally we require, if you have as many data as available, that much accurately you can predict the drought. So joint probability is the probability of both events occurring together based on observed data rather than theoretical assumptions. Empirical joint probability refers to the probability of two or more events occurring together based on observed historical data rather than theoretical assumptions. It is calculated by analyzing past data to estimate the likelihood of different conditions happening simultaneously. For two events A and B, the empirical joint probability is given by probability of AB equal to number of times both A and B occurred divided by total number of observations. Probability of A and B equal to number of times both A and B divided by total number of observations. This is estimated from a data set where occurrence of both events are occurred. Then identifying relevant variables. To predict drought, we consider meteorological data such as rainfall, temperature, evaporation, hydrological data, river flow, groundwater levels, soil moisture data, vegetation health, agricultural impact, and climate condition like El Nino effects and their probability. Constructing joint probability distribution. Empirical joint probability is estimated using historical data. Suppose we have two key drought indicators like low rainfall or high temperature T. We define probability of R equal to probability of low rainfall, PT probability of high temperature occurring. Therefore, the joint probability PRT equal to joint probability of both occurring together. They may occur independently or they may occur simultaneously. Using historical records, we compute joint probability equal to number of years both low rainfall and high temperature occurred divided by total number of years in the data set. The data sets may be 10 years, 50 years, 100 years. If you extended this multiple variables like low rainfall, high temperature, and low soil moisture, we estimate PRTS. Previously, there were two variables. Here I am considering three variables. Number of years, all three conditions occur divided by total number of years. This helps in assessing how frequently drought conditions have occurred together in the past. And conditional probability in the drought prediction. In many cases, we may want to estimate conditional probabilities such as given low rainfall, what is the probability of a drought? Or if the temperature is crossing 45 degrees, what is the probability of occurring drought? Like this, we may estimate independently or jointly. So P D by R equal to P probability of RD and divided by probability of R. Given low rainfall and high temperature, what is the probability of a severe drought? PD by RT equal to probability of RT divided by probability of RTD. I have explained previously what is RT and what is RTD. These probabilities allow risk assessment for different drought severities. So the application in drought monitoring system, standardized precipitation index and Palmer drought sensitivity index uses rainfall and soil moisture data to estimate probability and drought conditions. And machine learning and statistical models, empirical joint probability distribution serves as an input for predictive models, and remote sensing data useful in predicting in finding the NDVI data and land surface estimation of land surface temperatures, and which are useful in the development of early warning systems for government and meteorological agencies use joint probability analysis for drought preparedness. And this is my mathematical equations which I adopted in this model here to estimate alternate to non-parametric, and I'm using Gregatron method. And again, my time steps are 1 month and 6 months. The empirical joint probability equal to mk minus 0.44 divided by n plus 0.12. And Gregatron plotting position can be expressed as I minus 0.44 divided by n plus 0.12, where n is the number of observations, mk is the number of pair occurrences. And third method is artificial neural methods. An artificial neural model is a computational model that uses mathematical equations and numerical techniques to simulate real-world physical, mechanical, or natural resources. These models are artificial because they do not arise naturally, but are instead designated by humans to approximate complex systems. Components of an artificial numerical models. A numerical model consists of the following key components: mathematical formulation, numerical discretization. So in the mathematical formalization, we may use differential equations or algebraic equations, which represents physical laws such as conservation of mass, momentum and energy in fluid mechanics, Hooke's law in structural mechanics, and heat conduction equation in thermal simulations. And numerical discretization converts continuous equations into discrete form, making them solvable using computer programming. And common techniques are finite difference method, finite element method, finite volume method, and mesh-free methods. And initial boundary conditions required are defines the starting state of the system, specific constraints such as fixed support in structures or inflow-outflow condition for our river flows. And computational solutions using numerical algorithms like Newton-Raphson method or Gaussian-Seidel method to find approximate solutions, and which requires iterative solvers when dealing with nonlinear problems. And validation and calibration compares numerical results with experimental or real-world data, adjusts parameters to improve model accuracy, and whatever I said, the theory I fit in an equation form, which was ykt equal as a function of sigma j equal to 1 to m activities, which is a function of all that variables. And last one, standardized drought analysis toolbox SDTD model is a computational tool used for analyzing and monitoring drought conditions using various standardized drought indices. It integrates multiple data sources, statistical methods, and visualization techniques to assess drought severity, duration, and frequency. SDIC calculations includes calculation of SPI by measuring drought severity based on precipitation, computed at different time scales, 1 month, 3 months, 6 months, by using the formula SPI equal to P minus mu sigma SPI divided by P, where P observed precipitation, mu mean precipitation, and sigma standard deviation of the precipitation values. And standard precipitation evapotranspiration index SPEI incorporates both precipitation and temperature for drought analysis, more accurate for climate change impact studies. And Palmer drought sensitivity index based on a soil moisture balance equation used for long-term drought needs. And reconnaissance drought index considered both precipitation and potential evapotranspiration. And the workflow in the SDT is collect meteorological and hydrological data sources from NASA, NOAA, IMD, or groundwater department. Remove missing under processing, remove missing values and normalize the data. Convert raw climate data into a standardized format and compute drought indices by SPI, SPEI, PDS, RDI. apply statistical transformations to compute drought severity, and visualization and mapping, generate time series plots of drought variations, create GIS-based drought maps using spatial interpolation, and decision making and policy recommendations, use results for early warning systems and disaster management strategies. So this is the SDI model which I adopted in my study. I use gamma distribution. Again, time steps are 1 month and 6 months for prediction. The gamma probability density function is defined as 1 by beta power alpha into gamma alpha into x by x to the power of alpha minus 1 e power minus alpha by beta. And the gamma distribution equal to 1 by gamma alpha integral 0 to x t power alpha minus 1 e power minus t dt, where alpha and beta are shape and scale parameters of gamma distribution. The cumulative probability Gx can be simplified to gamma distribution function assuming time step t equal to x by beta. Okay, so whatever I explained the 4 methods, the data sets and the process and the equations. So now I'm presenting my results of the study. So the mean decadal water levels of the National Hydrological Station Gujarat and Daman of the phreatic aquifer for pre-monsoon period from 2007 to 2016 you used for the drought assessment, and some data I'm using for assessment, some data for model generation, some data I'm using for model validation. With the help of groundwater data, a standardized groundwater index (SGI) has been calculated, which is shown in the figure. On the x-axis, hydrograph stations of all districts, numbers of the study area, and y-axis, depth of groundwater in meters. The maximum groundwater depth is for Anand and Daman districts, and the minimum values is found for many districts such as Amreli, Dayu, Kutch, and Sabarkand. And these are all the standardized groundwater index graph. And next one, on the x-axis, there is a number of hydrograph stations in all districts, and on the y-axis, drought occurrence. As a result, the highest probability was found on Bharuch district, and the minimum probability was found for Surat and Surendranagar district. So this graph will depict probability of drought occurrence. On the y-axis of the probabilities, probability starts from 0.1 to 1, and these are all my months on the y-axis. And next one, standardized groundwater index from SD80. By combining both previous two, I'm generating the standardized groundwater index map. So on the y-axis, standardized groundwater index, and x-axis I have the time steps. Okay. Then after independently calculating all the indices, now I'm estimating the probability of drought occurrence due to sensitivity of the soil from the month of May to October. So I've assumed different sensitivities for different months, sensitive 1, 2, 3, 4, 5, and 6. So each and every month, how the probability of ground soil moisture variation I have presented. And this information will give you the probability of drought occurrence due to soil moisture conditions. So again, for different each and every, I told you my time step is 1 month and maximum period is 6 months. So each and every month I'm estimated, and I have results are presented. And mathematical curve fitting of all the 6 months. These are all the 6 graphs will give you the mathematical curve fitting of the values. So the results of standard precipitation SPI, standard soil moisture index SSI, multivariate standard drought index empirically MSDIE, and multivariate standardized drought index parametrically MSDIP as depicted in the four graphs. So method 1, method 2, method 3, and method 4. And this figure shows the that is the previous one, independent one, this method in one graph. I try to compare all the 4 methods. So, for the 6 model for 6 months. The green curve shows the SPI and the blue curve for SSI. I have given the index here. So it's noted that SPI, MSDI, and MSDIP showed significant variation compared to SSI. SSI means blue color. This is the blue color. All the three methods are they are varying very high about the mean value for the different years from 1980 to 2012 with the groundwater index. That's what about 4 statistical methods. Then your AI models. For the design of AI models, it is crucial to fine-tune the model parameters to find the optimal setup. The best architecture of drought prediction of AI is that develop a mathematical algorithm and inspect it thoroughly. A two-layer feed-forward network with hidden sigmoid neuron and a linear output neuron can fit multi-dimensional mapping problem arbitrarily well, given consistent data and enough neurons in its hidden layer. It is just architecture of my programming. The network is trained with a scaled conjugate gradient propagation algorithm. 3 kinds of samples used in the network described as follows. For training of my data, 80% data, the number of samples trained and presented to the network during training and the network adjustment according to its error. And for validation, I have taken 10% of the samples data, and for testing, I am using remaining 10% of the data. The mean squared error is the average squared difference between output and target. Lower values are better, and zero measure means no mistake. My model is working very good. So figure shows the mean squared error reached a minimum in 7 epochs, means 7 iterations. Blue color for training, green color for validation data, red color the test data, and dotted line is the best value of my different epochs. The figure shows 4-layer of neural network training set state plot for the network with 4 input nodes and 10 hidden models and 1 output node with a combination of structure 4, 10, and 1. The training stopped when the validation parameter reached 6 validation checks at epoch 13 with the gradient descent value 0.31978, which would cause the convergence of network fast. So this is the validation checks at epoch 13, and this is the validation again checks gradient of 0.3197, which I got as 61. This is for gradient, but the below diagram gives the your failed epochs, epochs. Mean I'm not getting accurate data for the other set of data. Data graph also have error graph also presented. That is known as error histogram. Error histogram is another tool used to obtain more information about the neural networks. It is clear from the figure that the validation and test results are acceptable and the error distribution results are reasonable. In addition, the constitution gives a good indication of values are outlier. Nevertheless, these outliers do not affect the results because they have only few data out of the total data, and most error false is 0.06103. The blue bars represent training data, the green bars represent validation, and the red bars represent test data. The histogram can indicate outliers, which are data points where the fit is significantly rose than most data. So this is what I'm explaining my error histogram. This is for training and validation and testing, and this year I got the 0 error. So finally, for any statistical data, the accuracy depends upon what is the R-square value, measures the correlation between output and targets. An R-square value of 1 means a close relationship and 0 a random relationship. In following figure, the 3 plots represent the training, validation, and testing data. The dashed line in each plot represents the perfect result output, that is minus output equal to target. The solid line represents the best fit linear regression line between outcome and targets. The R-square value is an indication of relationship between the results and targets. If R-square value indicates there is an exact linear relationship between output and target. If R-square is closer to 0, there is no linear relationship between output and the target. So this is the neural network regression curves for training, validation, and test data. This is the best validation performance is 0.0029 at epoch 1000. 1000 trials, 1000 times I'm iterating my data. blue color training, validation, and best dotted line is the best one. So all the data I'm getting approximately all things are parallel. Okay. So in conclusion, the average groundwater depth, maximum pre-monsoon in the area of Anand and Daman, and minimum pre-monsoon season, Amreli, Dayu and Sabarkan, and the probability of drought occurrence, maximum in Bharuch and minimum in Gandhinagar and Jonagar, and standard water level index SWI is maximum for Banaskantha and Daman and minimum Porubandar and Rajkot, and risk assessment due to sensitivity of soil moisture, maximum in month of May and minimum in the month of October, and probability due to soil moisture in the month of May, maximum almost all districts and minimum in very few districts. Probability due to soil moisture in June month, probability of occurring the drought, maximum in Bharuch and minimum in Surat. Probability of drought due to soil moisture deficiency in July month, maximum in Kutch, minimum in Anand, and probability of occurrence drought due to soil moisture in August, September, and October months. Similar results in all the in my study area. Okay. Therefore, Western Gujarat more prone to droughts than eastern part, and more probability of drought found in May month than in the least found in the October months. So these are all some of my references which I used in my study. So thank you, sir. This is what I would like to share my students some of the study on this.
Thank you, sir. Dr. Nagamalleswara.
Thank you, sir.
Excellent presentation and giving us a depth into the subject of predicting the droughts by using the methods of artificial neural networks. And the case study was really very pragmatic and very informative and very useful to the all those who are related with the subject. And thank you, sir, for delivering this lecture. Sir, there are two more, just a small this. After that, can I go for question and answer?
Yes, sir. Please, sir. If anybody can, I can try to.
Actually, we want to invite Ramagundam Chairman, Mr. Apparao Garu, also to small address. So I request Apparao Garu, kindly deliver your address, sir. Apparao Garu.
Good morning to one and all, sir. On behalf of Ramagundam Local Center, I wish Happy Republic Day to all the participants. Thank you, sir. Thank you very much.
So would you like to give a small message?
Sir, due to this, I am in the outside. I am unable to speak now, sir. Please
Okay.
continue. Please continue.
Okay, right. Thank you, sir. Thank you. Thank you for giving association with our center. Now I request the family members, Madam Anuja Garu, and I don't know any other family member is available. So kindly, would you like to say about your father, madam?
Yes, thank you, Andy, for the opportunity. Really appreciate it. And thank you for the presentation. Dad would have really, really enjoyed it, especially the technical aspects of it. And we're really happy that you guys are doing this presentation every year. Thank you.
Thank you, madam. Thank you. Now, sir, anybody has any questions, please, our keynote speaker is ready to answer. Rameshwar, you have any questions, please? Rameshwar Garu.
No questions. I'm very happy that just now we had the daughter of SUBBA Rao sir, because SUBBA Rao sir is in our department. He worked in HMW, SSB. He is very always used to conduct many technical programs, and also one technical handbook also prepared by V. SUBBA Rao sir, because I worked him in HMW, SSB. Thank you very much. The talk is very nice and it is very informative and also very research. This is very much useful for the research students. Really, thanks to the chairman for giving this chance. Thank you very much.
Yes, sir, welcome. Anybody, any questions, please? Anyway,
Sorry,
if
sir.
no questions,
Chari sir. Anmanda sir.
sir, if no questions, I will move further. And any questions later, if arise, you can write to the Telangana State Center. We are having a number of our Dr. Nagamallesh Rao, sir. We can forward to him and he will give answers. Okay, sir. Now I request our Honorary Secretary of Ramgundam Center, Engineer Srinivas Reddy Garu, to propose vote of thanks.
Good morning, sir. Good morning. I'm very happy and privileged to present vote of thanks, sir. Am I audible, sir?
Yes, yes.
You are audible. Please go ahead.
Okay, sir. Good morning. Respected vote of thanks. I am very happy to present vote of thanks, sir. Respected keynote speaker, Dr. Nagamalleshwar Rao, MIE Professor and Head, Department of Civil Engineering and Associate Dean, CVR College of Engineering. Engineer B. Brahmareddy, FIE, IMM Chairman, IEI TAC, today's presiding chairman. Engineer P. Apara, FIE, Chairman, IEI, Ramgundam Local Center. Murray Ramesh, FIE, convener of the event. Dr. ISN Raju, FIE, Council Member, IEI. Dr. SN Rao, FIE, past Vice President, IEI and past Chairman, IEI, APSC. Dr. Hanmanchari, FIE, past Chairman, IEI, APSC. Galaxy of eminent personalities, past Presidents, past Chairman, Council Members, Committee Members of IEI, TSC, Corporate Members of IEI, Family Members of late Engineering, B. SUBBA Rao, media friends, ladies and gentlemen, good afternoon to all. On behalf of the Telangana State Center of IEI and on my own behalf, I convey our sincere and profound thanks to the Dr. B. Nagamalleshwar Rao, MIE Professor, Head and Department of Civil Engineering and Associate Dean, CVR College of Engineering, Hyderabad, for delivering the E.V. SUBBA Rao 8th Endowment Lecture on predicting the droughts using artificial neural networks, a case study. Really, sir, it is a different subject for mining this one, and predicting the droughts is very, very important, sir. And today is also Republic Day. On this special day, as we celebrate our Republic Day, let us also take a moment to reflect on the power of unity, knowledge, and the Republic Day reminds us of our collective responsibility to make India stronger, wiser in every way possible. A big thank you to all the attendees for your participation today. Once again, I thank Nagamalleshwar Rao Garu for his valuable time, sparing his valuable time for sharing his expertise with us today. On behalf of everyone here, I extend our warm Republic Day wishes to all, and may we strive for a better and more prosperous India. Thank you. Now I request to raise for national anthem. Thank you, sir.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, sir, and have a wonderful day.
Thank you, sir.
Sir.
Thank you.